Hey everyone, my name is Votipka. I'm a PhD student at the University of Maryland, and today I'll be talking about some of the work that my colleagues at Maryland, Tufts, and Syracuse University did titled an observational investigation of reverse engineering processes and mental models. So I'm talking about software reverse engineering. I'm talking about basically looking at someone else's code to figure out how it works. And uh, in security, this generally means you're doing vulnerability discovery. For example, maybe as part of a bug bounty program like HackerOne or BugCrowd or other vulnerability disclosure program. Or you're looking at malware analysis, for example, looking at the WannaCry ransomware or Stuxnet worm, trying to understand how it works and either mitigate its effects on a system or defend other systems from being infected by that malware. And this is generally a complex task. There's a study by Yakton et al. Back in 2016 where they had 30 participants try to perform basic reverse engineering tasks on small programs, about 150 lines of code, and it took on average about 39 minutes. So this can get really complicated. And there's several tools available, sophisticated tools developed by academia and industry partners, but these are generally built sort of on an ad hoc process based on the developer themselves, intuition, and prior experience. And this is because there's just really limited theoretical model for how the reverse engineering process works. What are reverse engineers' actions, habits, mental models? There's been limited work in this space. And so our goal specifically was to sort of fill this gap. We wanted to develop a refined reverse engineering process model to guide future tool development so we can start to build better, more usable tools for reverse engineers. And there's actually an area of work that is related to this. While there's been limited work in the reverse engineering space, program comprehension has actually seen a significant amount of work. And this is specifically looking at how developers process unfamiliar code during the modification and maintenance and debugging tasks. And what this work has found is that developers generally approach the programs in a nonlinear fact-finding perspective, trying to test different hypotheses and questions, and sort of moving around in sort of this nonlinear way. And as they go through, they scan for patterns called beacons that allow the reader to quickly infer how the program behaves. And they do this sort of scanning process as well as just trying to understand and answer these questions through several different simulation methods, like running the code, reading it statically, dynamically, things like that. And so one thing you might be asking yourself is, well, is the reverse engineering process any different? There's no access to source code, developers, or documentation, so you're actually operating in a more resource-starved environment. And also, reverse engineers generally operating in a more adversarial environment due to obfuscation or other anti-debugging techniques. So we do believe that it's likely the case that there are differences. But that leads us to our main research questions. First, what are the high-level processes that reverse engineers follow? What are the steps? What are the mental models? What are the technical approaches that they use? And are the RE and program comprehension processes actually different? And now for this talk, I'm not going to go specifically in those details. There are differences that we identified, but those are given in the paper. Now, to answer these questions, we performed a series of observational interviews, and these are using a protocol taken from the naturalistic decision-making world, which is the study of how experts perform tasks sort of in the real world. And so we took the critical decision method protocol, which was proposed by Klein et al., and basically has experts go through and describe a recent event. And this helps with recall of certain things. We also modified this so that we have the reverse engineers actually demonstrate. So they shared their screen with us and they demonstrated the reverse engineering process so we could get a better view of exactly what's going on. And as they went through, we noted and asked further questions about certain items of interest, mostly taken from the program comprehension literature, so those beacons, hypothesis questions, and simulation methods, but also the decision methods. How did they pick, or decision points? How did they decide what code they were actually going to look at? And resources. So did they go look at Stack Overflow as an example? And we performed 16 of these observational interviews. And this slide shows all the demographics for our participants. And I'll note participants were generally more experienced, having on average 9 years experience, and rating themselves on a scale of 1 to 5 for their skill as about 4. And our participants were split between vulnerability discovery as sort of their main task for reverse engineering and malware analysis, with one participant reporting both as something that they did sort of evenly. So what do we find? What was the actual process? Well, we observed that there was actually sort of a 3-phased model that our reverse engineers followed, with these 3 components shown on the screen. And I'll go through each of these in detail through the rest of this talk. So our reverse engineers began by looking at the full program, and they tried to get an understanding, sort of an overview of how the program is structured, generally what it does, doing things like listing the strings and APIs used in the program, running the program under sort of basic parameters, and reviewing its metadata. And the goal here is to identify specific functions and code segments that they want to focus on in more detail that might be of interest to their specific goal, either vulnerability discovery or malware analysis. Then they moved into the subcomponent scanning phase, where participants were looking at segments of the code, doing things like, for example, scanning for beacons or patterns. So one example of this was given by a participant who looked at this code and first saw this as there are these 2 sets of strings and said, well, it's just trying to make a connection to each of those websites. Just based on their prior experience, they knew that that's what these strings most likely identified. Then they saw this integer here at the bottom and said, well, if it's able to make a connection, it's going to return a non-zero value. And then based on these 2 pieces of information, they summarized all this code to say, well, you usually see this if malware is trying to see if it has connectivity. And so they, in a few seconds, were able to determine that this function is just a connectivity check for malware. In addition to scanning for beacons, as participants go through and sort of skim through the program, they might also look for or scan specific data flow and control flow paths. So an example of this be this code where a participant might ask, well, can I free undefined memory? So can I get to a point where X is not defined, but it's called to be freed here? And so they first want to look at the control flow paths. They scan the first control flow path here, see that X is defined as Y, and so this whole path can be thrown out. I don't need to look at any more of this code. Move down to the next one. X is not defined, so let's continue to dig. But we need to also pass this check where val is equal to -1. So now the participant would only look at the data flow to this instruction for val and sort of skim over all the other remaining code. They'd see that val was set to A and A was set to -1, meaning that it's impossible to get to this, this call to free without having X already set. And so they can move on to their next hypothesis or question. And as they go through this scanning, they learn more about the program. And at some point, they might have a specific hypothesis or question that requires some concrete information. And at this point, they moved into the focused experimentation phase, where they're looking at a specific execution trace or a few lines of code. And in this phase, they're trying to test specific hypotheses and produce concrete answers back into the subcomponent scanning phase. And they do this through things like executing the code under inspection using either a debugger or packet capturing or file monitoring tool. They might compare the code to a reference implementation. So if they think, for example, it's an encryption function, they might go and implement that same encryption algorithm in their own code, run the code on the same inputs and see if the same outputs are produced. And then finally, they might just go and read the code line by line, mentally simulating sort of what's going on in that program. But I want to note that we saw participants use this very rarely and not on very many lines of code. So the max was 50 lines of code, and that was sort of the outlier in this case. So participants rarely use this on anything beyond a few lines of code. In addition to sort of this process model, we also saw a few cross-phase trends. So for example, when we look at the methods that were used, we saw that the first 2 phases used mostly static methods, whereas the focused experimentation phase, participants tended to switch into a dynamic or to use dynamic tools or dynamic processes. And then we also saw that experience plays a role throughout all three phases, but in slightly different ways. So for example, in the first two phases, participants relied heavily on their experience to choose which parts of the program to actually focus on. Then in the subcomponent scanning phase, they used their experience to sort of have a library of patterns or beacons that they were looking for, and also understand when a vulnerability might occur. And then throughout, they used their experience to pick out which method would be best to use in the specific case. And then also across all the phases, we saw that whenever one of the participants used a tool, it was often for the purpose of improving the readability so they could add comments to the code or just make it a little easier to understand. So what can we actually take away from this now that we have sort of this understanding of the reverse engineer's process? Well, this can help us to build guidelines for a more usable tool design. We actually provide 5 guidelines in the paper, and I can point you to that for more reference. Additionally, this is helpful as a framework for tool evaluation to see whether or not a new tool or an existing tool fits within the model and is likely usable by a reverse engineer. And then also provides insights for reverse engineering automation to help improve the human automation interface. So with that, I will close. So in summary, we identified a 3-phase model, specifically broken into 3 pieces: the overview, subcomponent scanning, focusing on experimentation phases, several cross-phase trends and takeaways. And I'll like to thank all my colleagues, our sponsors, and I look forward to taking your questions.